In this video, we will be assessing a car shown in figure Q4 that is on an inclined road surface. We've been told here that the car is held in static equilibrium by a cable that is in tension, this cable here, and that the contact between the wheels and the road surface is friction-free. What this means is we do not need to consider friction in this instance. So part 4a of this question is asking us to just simply draw the free body diagram of this car. So let's go ahead and do that. Part 4a, and let's make sure that we make this diagram nice and big. If we draw our car at a slight angle and make it a box, because I am no artiste, and note that this time, unlike some of the previous videos, we're going to be labeling our axis like so. And this is simply so that we can remove some of the complications that arise when working at an incline. As we write the forces down, you will see why this might make sense later on. We have our reaction forces of the wheels here, make that a bit more visible, here and here. And this is implied that we need to consider these given that the car is held above the ground and that we've been given these lines here. So let's go ahead and do that. Let's say that we have a reaction force here and here, and given that we've been told that it's points A and B, let's call that RA and RB. We also know the mass of this car to be 5,000 kilograms, which is 5 tons. But for it to be a force, we need to convert that into a weight, which is just simply multiplying by the gravitational force. So from the center, from here, not that it makes a difference really when drawing a free body diagram like this, just simply to indicate the forces, something straight down, we will label that as 5,000 G. Remember, 5,000 times our gravitational force, which is just, let's write it in brackets, mg. And finally, we can't forget the tension, of the cable that's holding this car in static equilibrium. So let's go ahead and draw this in, like so, as T. And there we go. That is our free body diagram. Nice and big, easy to manipulate. Part B of this question is asking us to calculate the reaction forces of the road surface on the tyres and the tension T in the cable. So if we hadn't added in RA and RB in our free body diagram, we know to do that now, as we are being asked in part B of this question to find the reaction forces of the road surface on the tyres and the tension T in the cable. So the nice thing about drawing our frame of axis at a slight incline is that it makes our reaction forces just slightly easier to deal with. So in part B of this question, again, like all of these questions, we are in static equilibrium. Let's consider the forces acting horizontally and vertically. Fx, leave some space for any work we might want to do, and Fy. So let's start with Fx. We know that we are in equilibrium, and if we assess the forces acting in the x direction, we know that we have T cos, and tension is 20 degrees. So let's write T cos 20. And we also know acting in opposition to that here, we have minus 5,000 G sine 30. And it's sine 30 because of this angle here. And again, nice reason that we have these axes is because, yes, these angles are different, but when we change our frame of mind, when we tilt our head a little bit, we can see how these angles can be related to cos 20, t cos 20, and 5000 g sine 30. So through a bit of rearranging, already we can find the tension T in the cable. And before we do that, we are in static equilibrium. Let's go ahead and set that equal to 0 so that we can rearrange. So we can say that T cos 20 is going to be equal to 5000 g sine 30, and through a bit more rearranging, we can see that T is going to be equal to 5000 g sine 30 divided by cos 20. And I will leave it to you to figure out what that number is exactly. Okay, so that's us dealt with the x direction. Now let's go ahead and look at the y direction. In this case, again, tilt our head a little bit, the horizontal direction, the vertical. We know that we have our reaction forces, RA and RB, acting with our positive y direction. So let's go ahead and note that down, RA plus RB. And in addition to that, our tension force is acting also, our component of our tension is acting this way, upwards, with the y direction. So bearing that in mind, we are also acting in the same direction. Let's write that as T sine 20. Also to note that we are acting, the weight of this vehicle is acting downwards against the y direction. So we're going to note that as negative 5000 g, and in this case, cos 30. Again, static equilibrium, let's set that equal to 0. If we rearrange that, we can see that we get RA plus RB plus T sine of 20 is equal to 5000 G cos 30. So these are the forces balanced, everything acting in one direction, the positive direction, is the same as the forces acting in the other direction here. So through a bit of rearranging, given that we already now know T from this up here, we can plug T into here and rearrange to get that RA plus RB is equal to 5000 G cos 30 minus T sine of 20. And this might not seem very helpful right now, and we might be at a bit of a loose end, but given that we have reaction forces and we are acting on a slope, chances are there's one more thing that we need to consider.